But then it has to be the two of us.
No, I'm not expensing anything. So you are expensing. No?
That's true.
Okay, no.
Yeah, yeah. But you don't want to appear the two of us here because we.
We can.
No, but anyway, we.
Bueno, ya hago aquí un mute, subo otro que se llama.
Hello, everyone. Christian, is it time or not? We're waiting for the boss to give the go ahead. Should we start?
And we are recording already.
We are recording. Oh. So hello everybody, welcome to NetBCN, our main event for February 2000. This is March, but where it's March already?
It's March.
March 2026.
So it's our biggest event.
Our biggest event of normally of the year, or not? The one of the together with the Mobile World Congress. I'm pretty sure this is more fun than whatever they're showing in FIRA, right? Yeah, so for anybody that doesn't know the group, probably you do because you're here. But anyway, this is NetBCN. We have been working here for a few years, right?
It's 10 years this year.
10 years. Time flies when you're having fun, right? We started a Meetup. Now Meetup tried to drain us from too much money, so we are independent. We became independent. We're doing what we can. And today we have this great event. Let's see. There's going to be a bit of a change in the agenda. Xavi will still start, but then Ivan Pepelniat couldn't make it, probably because of some reason for his flight. So then Christian is, oh, this one is updated, right? Oh, no, okay, yeah. So Ivan is going to talk online after Xavi, and then the agenda will resume as it is. And Christian will go to the 5 o'clock slot. Paolo, come on.
Yeah. This is the continuation of the agenda. We have a fantastic speaker. See, take a picture for our boss, so that. And so, as Camilo was saying, we are the internet community in Barcelona. So if there is events related, probably it's the biggest event related to networking, right? We try to organize one every 2 to 3 months. This is probably, the biggest. The other, there is less attendance. Maybe they are more specific on some specific topic. We start later in the evening. If you have anything to contribute on or to talk about in any of these events, please, we are always happy to get proposals and join us. And this is how to be in touch with us. So on the first, it's our website where we essentially post the agendas and the new events. The other, it's just a little bit more static. It's an introduction about us. Our main way to stay in touch with us is with Slack, and then email if you want to reach the organizers by email. You have proposals for an event or for some presentation. And of course, this event could not be possible without our sponsors. So thank you to Arista and Musefes, which are sponsoring the coffee breaks that we are going to enjoy over some talks. Thank you to USC, to Pere, for hosting us in this beautiful place, for this event. And that said, at the end of the event, so that all of you stay, not because of the beers. I don't know if there is beers, but let me say that there is beers at the end. There will be a raffle of the books that, I don't know, it's the 10 book that Christian is writing about network observability. And so there are a few books there. We will be a raffle, and we will use this time of the event to find an algorithm to how to do this raffle. Because we don't know yet, because there was the idea of doing a raffle, but then I said, how do you do the raffle, Christian? And he said, yeah, we do something and whatever. So we are going to engineer a fair algorithm in, the three of us, also you, because you are a PhD, so he will do a lot of work. And with this, Xavi, where are you, if you can come for the presentation.
Let's go. Okay, so my name is Xavi Oms. I've been in the networking side of the industry for, 20 years. No longer there, so I've been in cybersecurity for the last 12 years of my career. So it's kind of diverging from networking, but even so, Christian thought that it may be interesting for me to share some experiences of what we're doing right now in our unit inside Palo Alto Networks. So you may know Palo Alto Networks is a cybersecurity vendor known by the firewalls, but we have many other things. And I'm a member of what is called the Innovation Office inside Palo Alto Networks. So we do everything that no one wants to do. So yeah, it's something that needs to fail fast, something that needs to, make a hypothesis on areas, something that needs to analyze opportunities. So we're doing basically experimentation. And one of the experimentations we've been doing applies to AI ops, so operations by AI. In our case is in networks, in cybersecurity operations, but obviously it applies as well to network operations. So what I'm going to share with you is a methodology we've created internally. It's still experimentation, so it's not yet in the products, it's not yet being used. But it's something that we built here in Barcelona, and we are exploring to be used in our products, in our operating systems. And it's based on a small, really small, I will say tiny models created for a specific domain of AI operations, and so small, so tiny, so fast that can run on CPUs, on general purpose CPUs, which means that you can deploy those models in any CPU, in any switch, in any router, in any firewall, in any device, and make inference of those models inside the device itself, which provides or opens an array of opportunities for observability, for autonomous operations, for self-healing, for things like that. So that's what I'm going to share. I will not be able to join you on the coffee breaks or with the beers. So I will try to make my presentations 20 minutes. So we have 10 minutes left for the next presenter, or if you have any question, for having those questions being debated on the presentation itself. Otherwise, I will not be able to debate with you after the presentation. Said that, when you think about, so this is basically our thought model, right? When we start thinking about AI operations using AI for improving how the networks, our firewalls in this case, will react to state changes and self-heal themselves or things like that, we realized that using general purpose or general AI for this use case was a no-go option for many different cases. But the most important one is latency. So if you have to engage with an LLM or a big model for data that is created at control plane speed, meaning hundreds of events per second, it's not going to work, right? It's not. The latency of the models providing inference is not going to pace at that rhythm. But there are other things, like for instance, what about if the access to that model is down and you rely on that model for self-healing? It's obviously something that will not work. And also there is this precision thing. Those models are crazy, they are great, they are super good, but when you try to apply those models that has been trained on things like Bill Clinton being the president of the United States, what do you care about that when you are trying to decide if this log generated by this firewall or this switch, it means that the device is going to a state that is no longer stable? I mean, it doesn't mean anything, being trained on those things. So we realize that even if they are super good and trained on many things, when you try to apply those models to something that needs to be really, really precise, because you want to decide that the device should take this action or modify himself and do whatever because he's detecting that the state is going to somewhere that you don't want to be, you have to be sure that that's the right decision to be taken, right? I mean, and that's when precision comes into mind. So for many different reasons, we realized that using general purpose AI models was not the way to go. And then the next thing that came to our mind, and this is something I have to share with you to settle. The presentation is really technical, it's really deep. I hope it meets with the audience here, but I need to clarify a specific bit of what AI or models are to understand the rest of the presentation. So when we think about models, typically we think about what we refer as a decoder model. ChatGPT, Gemini, all these things that we have in mind, they are decoding models. They generate things. There are other, I mean, in reality, they are encoder-decoder models. But there is another type of models called the encoder models that they are meant to basically, as the word says, encode something, a context, into a component called an embedding. An embedding is basically an array of float numbers. So you can imagine that as a vector in a multidimensional space. And one encoder, compared to a decoder, do not have things like hallucinations. The same context, exposed to the same encoder model, will generate always the same vector, always. No hallucinations, it's a model designed to take this input, process the input, and encode that input as a vector in your dimensional space, and it will do exactly the same operation over and over and over. For the same input, you will get always the same output, no hallucinations. So compared to a human, an encoder can take a big, large input context and map that input context into something, a vector, a place in the space. It's something that a human has a hard time doing that. So when you try to put a human understand what these, I will say, 1,000 events means, events from a firewall, from a router, it will, try to find what's important in that list of 1,000 events, find something that is relevant to him, and then he will try to look forward, look backward, and try to find the context on that. And it will have a hard time. It will take a long time for that human to do that. But encoder model trained on a specific domain will look at that 1,000 events and spot exactly what's going on there based on the attention mechanism, and it will provide you, you will be able to use the embeddings generated by that model for many different use cases. Questions? No? So what I'm going to talk about you is encoder models. No decoders, no chats, no AIs. Let's keep talking about those things. No. I will provide you something. It will be a context window of events. And I expect from you model to generate for me an encoding, a vector dimension of what that context window means. So the next thing that, when we had that in mind, we said, okay, cool, there are many encoders out there. The most famous one is BERT, B-E-R-T. It's the most famous encoder in Hugging Face. There are many others, but if you look at Hugging Face and look for encoder models, trying to not reinvent the wheel, use a model that is already there, a model that can generate embeddings, can generate encoders, you will find that all of them share the same tokenizing strategy. So they will get whatever input you provide to them, and they will split that input into tokens. And the way that the input is tokenized is done with different algorithms. The most famous one is the BPE, byte pair encoding. I see really faces that you don't know what I'm talking about. Is that okay? Is someone knowing what I'm talking about? Or okay, so I mean, I'm trying to model. So the tokenization is, I mean, a model requires numbers. 1, 2, 11, 43, 1,000, whatever. A model, an AI model works with numbers. So you have to convert whatever the input is, an image, temperature, I don't know, whatever, into numbers. So tokenization is the process of converting whatever you have into numbers. And the most common tokenization is trying to look for pairs of bytes. For instance, 10, 1, 0 is super common. So instead of tokenizing, I mean, one easy way of tokenizing text is by replacing each char by its ASCII number. But you will have a small dictionary, 127 words in the dictionary, but the input to the model will be huge. Imagine 1,000 events, one position per each character. The input is going to be huge. So you try to compensate that with a bigger dictionary. Instead of only 126 chars, let's look for common pairs. 1, 0 is a common pair, so I will create a token in the dictionary for 1, 0. And I will enlarge the dictionary, will make the dictionary larger, but in return, I will have a smaller input. So this is what the general purpose tokenizers do. They've been trained, the tokenizer, not the model, the tokenizer has been trained on huge amount of text, and the tokenizer has found that the 160 ... is something so common that deserves a token itself. Or the ion space equal, it's something as common as well that it deserves a token for themselves. So that's how tokenizing works on any model that is in Hugging Face. And when we look at that tokenizing strategy, we realize that, come on, I mean, a log, it's always the same template. I don't care about this equal. And I don't care about ALLOW. There are only 5 states or 5 actions: allow, deny, drop, and whatever. So why the hell I am encoding ALLOW as different things when at the end of the day is a small set of potential values, it's an enum. So we thought, what if we question the basis of everything and we create our own tokenizing strategy, a domain-specific tokenizing strategy that if at the end of the day we are going to tokenize events from our specific system, let's say a firewall from Palo Alto Networks, I do know that this is the format, this is the different options for allow, this is the different options for protocol, this is the, I mean, it's a finite number of opportunities of values on each entry, so I can create a much structured dictionary with a much lesser amount of tokens and create a specific, domain-specific tokenization of the input. There is a huge benefit on doing that. You will see just after this slide. The problem, if you do that, is this is the foundation of any model out there. If you replace the tokenization for your own tokenization, the model is no longer valid. You will have to train your own model because you're changing the foundation of the model, which kind of scared us. Yeah, I mean, this is nice, it looks nice, but if we go that way, we are assuming that we will not use out-of-the-box models from Hugging Face. We will have to train our own model. And yeah, I mean, you've been heard, this is scary, how many GPUs do you have? How many years of training, how many computing power do you have to train your own models? But we said, let's give that a try and let's see how far as I said to you, we are a kind of fail fast unit. So we try to, let's try and let's see if we can do that or if we fail. So we decided to, let's create our own tokenization and let's see where we go. So benefits about having your own tokenization strategy, a custom domain-specific tokenization strategy. The most obvious one is what we call the dimensionality reduction. 80% is what we got. So you don't have to care about 30,000 different byte pair encodings. It's what you have in the dictionary of BERT or common models. We reduce that. 80%. So our dictionary, our potential values in the dictionary, to map that to a number, to a token, it's small. It's really, really small, which means that whatever we fit in that dictionary becomes something tiny. The input to our model was no longer something big that required a huge context window, was something really, really small. So at the end of the day, what we got is something so small, so tiny, the input was reduced, the dimensionality was reduced so much that we started to think, okay, come on, maybe we can even target general purpose CPUs. Maybe whatever we get at the end of the road, the model that will be trained will be so small, so specific, it won't answer the question of who was the president of the United States. And no, I mean, it's going to be trained on a super tiny, narrow, domain specific. But on the other side, it will be able to provide inference, maybe, and we started to think, maybe in a general purpose CPU. So I'm doing a spoiler alert here. At the end of the road, we are doing, the model that we created for this specific domain is generating, I think it's 35 inferences per second on a Raspberry Pi. So that's what we got. And this is what an encoder model will do in our specific domain use case. The idea was to have a sliding window. So let's have a window of events, of logs generated by our control plane. Put all those logs in this context window in sequence, and let's expose the tokens from every log in the same window to a model that has been trained from scratch through different encoding layers, to different attention layers, to generate what we call the summary, the document embedding. We opt for a 128-dimensional embedding. Compared, I don't know if you're familiar with embeddings generated by ChatGPT or other models. Typically, the embeddings generated by those models are in the tens of thousands of dimensions. So we are talking about 128, a super small dimension. And that embedding has some features that resemble the hash that you do when you try to get a fingerprint of a document. When you have something, let's say a set of logs that you know that map to a specific bad behavior, you are typically tempted to do a fingerprint of that sequence of logs. So this sequence of log, I do a SHA-256 of that sequence of log, I get a fingerprint of that, a signature, and let's say that I have a database of known SHAs to known behaviors. And this is a very fast operation. Let's get the logs, let's do the hash, let's check if that hash maps to something that is known. And that works very, very well. So this vector, this sequence of 128 float numbers has that feature. You can store that specific vector in a database and attach tags to that value. But unless, different from SHAs, this vector do not change that much when the input slightly changes. In a SHA, in a fingerprint, if you change a value on any log, the hash that you will get, the fingerprint that you will get out of that will be completely different. It won't resemble at all with the original one. But using an encoder layer, the vector that you get, the sequence of float numbers, if you slightly change something, it will slightly change as well, but not that much. And if you consider that to be a vector, you can use what is called the semantic similarity comparison. And you may decide that, okay, let's assume that this vector is something pointing in a direction of the space. And I can map not only the point in the space with a specific tag, but the direction to that point. Because you will see later on that the direction, for instance, will be exactly the same if you have in one of those logs, let's say a crash, an exception. That crash, for sure, will be a direction on that space. So just for looking at the direction, for doing a cosine similarity with the vector, you can extract from this vector features like there is an exception in there, there is a BGP update in there, so just by looking at the dimensions, which is something that this fingerprint compared with a SHA doesn't have. So it has much more features, much more values. So what about training? So we thought, yeah, I mean, we have the resources, we are a company, Palo Alto Networks, so we wanted to go that route and train our own model from scratch. At the very beginning, we said, oh, yeah, but that's going to be very expensive, but okay, you're an experimentation unit, yeah, let's do that, and we will see how. The reality is it took us 1 hour at home. Sorry, 1 week at home. So the first iteration of the model, I thought, before I start doing that in the cloud, in Palo Alto Networks cloud, let me do some experimentation at home to be sure that I'm not, and I completed the training in 1 week at home. And I said, okay, cool, nice. And then I did some tests in our multi-cloud GPU, and yeah, you could train that in less than a day in a purpose-built data center with an array of GPUs. But yeah, doing a reduction of the input, using a purpose-built tokenizer, creating a small dictionary, choosing the right precision, the right amount of dimensions, 128 in my case. Yeah, the result is a pipeline that we use a technique called, a self-supervised technique called the mask language token for this use case. You basically, use millions of logs from your domain, and you follow a procedure of masking different tokens in the input and asking the model to learn from the context how to discover what token is missing. And at the end of the day, that's the training process, 1 week, one GPU, easy. Not that, it's not, I'm basically trying to tell you, this is not that complex. It requires the knowledge, it requires the team that has the computing science and the machine learning specific domain knowledge, but if you have the resources, go for it. It's not that complex. So what are we getting out of that? What we are getting out of that model is something that is called the state map or the heat map. I really don't know how to say that, but once you have the model, and that's we call that the foundational model, you provide the model a slide window of logs. That model, as said, has been trained specifically on that specific domain, and it will give you a vector on a multidimensional space mapped to that sequence of logs. Cool. And it will, as said at the very beginning, the same sequence of logs will generate exactly the same vector. So what we did after that is put some humans and some trusted tags into play. So we share with the model a sequence of logs that we know that is normal operations. And we looked at what point in the space that normal operations points to. And we repeat that thousands of times, trying to put dots on that multinational space, meaning something that is where the device is typically in. That's the normal state of the device. And you see the different logs always pointing to spaces or points in the space where you can tag those points in the space as this is normal. Then we repeat that with logs during, let's say, a maintenance routine or doing a software upgrade or doing different, and then you can basically tag, create points in the space that map to different operations in your device. We even share with the device abuses. So we, Palo Alto Networks, are a company that are in the radar of all the criminals for supply chain attacks. So they want to compromise our firewalls, because if they compromise our firewalls, then you're basically in customers' premises and you can do whatever you want. So we have tons of examples of people trying to abuse our firewalls, and we map those states as well. So when your firewall is under attack, where are you? How the logs map to different states. So at the end of the day, we have a map of all normal states in the firewall, which means that you can have a set logs coming into the model doing inference in real time almost in a general purpose CPU, and you can have a monitor looking where you are in the space. And while you are in known states of the space, you're good. But as soon as your sequence of logs makes the vector go into a direction that you don't like, or let's say even an unknown direction, you may generate an alert. Because I'm going to a point in the space that it's unknown to me. I don't know what that, I haven't had in my past any training example of a sequence of logs that point to that space. So it's something new. Maybe it's something unknown good, or maybe it's something unknown bad. So let's put a human in the loop, let's extract that sequence of log, let's put that in a queue of human operations, and take a look at that. What's that? Oh yeah, that's the corner case of you sweeping a networking card and putting, okay, good, so let me tag that point in the space, that's normal. Or no, oh shit, this is a brand new type of attack we've never seen before, or cool, interesting as well. So we can put some self-healing operations, or even asking the device to, if you go that direction ever again, shut down yourself. We don't want you to be compromised, kill yourself, and that's it. So things like that. So yeah, that's the promise of this project we've been working on for almost a year. It's what we call the self-healing device. So something that we could embed the resulting model into the device itself as a daemon, as a small software that could be fed with real-time control plane events. It could generate those vectors in real time and do the evaluation of those vectors against the heat map or the states that we know, providing a brand new way of dealing with unknowns. Right now, it's typically you generate events, those events became logs, logs go into a CM, CM generate alerts or automation, a human or automation will take an action, and that's the typical workflow. And we want to enable this new workflow where an event generates an embedding, a vector or a sequence of events generates an embedding, and then you do a state match against that vector and take an automated mitigation on the device itself, not without sending logs to. And if we do that, and that runs on the device itself, you don't care about this. I'm a small network or I'm a huge network. I really don't care. It's not about me having to do a dimensionality analysis of how all the operating center will look like, how many terabytes of logs do I have to collect on a daily basis. I really don't care. It's not the goal. For this specific feature, the device is autonomous. You don't have to send me the logs. So you can grow as much as you want. Make sense? Questions? And I think that's all. A summary here. There is a last note about the dictionary. All these, the foundation, all these benefits that we're getting from the model really start with a custom tokenizer and a custom dictionary. And I told you, if instead of using a purpose-built tokenizer, I create my own one, what's the drawback of that? The drawback of that is I cannot use any model, out-of-the-box model. I will have to train my own one. But that's applied to myself as well. So if I change a dictionary, the model that I've trained is no longer valid. So what if I was so strict on the dictionary that a software release that I'm about to launch is introducing a new action? So I told you there are not that many actions: drop, allow, permit, deny. What if in this software version we are introducing a kindly allow? What does kindly allow? It's a way of allowing, but just the fuck. Sorry, I don't know. I didn't account for a kindly allow. So I have to modify my tokenizer. I have to modify my dictionary, which means that my model is no longer valid. So do I have to rebuild everything from scratch? Yes. Do I care? No. It's 1 week time on a general purpose GPU. So I can create the pipeline and map the pipeline to the normal software release. So whenever you are at the end of your software release, when you're ready, run the training pipeline. And that's it. It will generate the new dictionary, the new tokenizer, the new model, and along with the software version, you will have your new model, your new inference, your new step map, everything. So it's not that the challenge.
Doesn't that change the states in your?
Yeah, it changes, but I mean the pipeline, the training pipeline is about getting the input, training the model, getting all the examples to generate the tags. So yes, you have a new model. All your training data will generate brand new vectors, but you know that this input maps to that state. So before, that state was on the dimension 3, 4, 5, and now it's a completely different space. I don't care. I mean, it's the process of training the model, training the space, generating the tags, all of that. So yeah, I mean, that's what we're sharing with the different teams inside Palo Alto Networks. We can stop looking at those big, nice, great models out there that do not provide the precision, are expensive to run. They have to be on the edge. There is no way you can embed the models in your device itself. They provide, and we can open the door to a cerebral AI edge models that has been trained for a really, really, really narrow, specific domain, specific task, and we can go there. It will be as small that we can run wherever we want them, a real-time inference model, and maybe we may be opening the door for a new era of self-healing networks where they base their own logs, their own events for state mapping and self-healing operations. So that's what I had to share with you. Hope that it was interesting. Any question? Any? Yeah.
Thank you for your presentation. It was very interesting. But I mean, for example, I can pick a tiny model, maybe less than 1 billion parameter, and I can use like Q LoRa to fine tune the model, and maybe I can. I mean, if I have the data, maybe I can end it up with a good model. I mean, but you are like using a very different approach. Do you think it worth it? I mean, for example, I don't think maybe you don't need to use a very different encoder. Maybe you can use a tiny model. These models are really great and are improving every day. I mean, the big companies are like launching every month a new tiny model. Using Q LoRa, for example, and good data, maybe I can end it up with something good. I mean, do you really think it justifies? You can justify the investment and the effort and the time you are using to do it?
So, I mean, so there are many different dimensions to that question. So first of all, there is a personal hate. It's something personal. I hate, from LoRa and all these strategies, to realize that at the end of the day, in that model that has been retrained or fine-tuned or whatever, I hate to know that deep dive inside that model, there is the answer of who was the president of the United States in a given year. I hate that. It's a personal hate, because somehow I'm spending CPU cycles for something that really, really, I don't care. So that's a personal hate. As of today, the other dimension of my answer is, even if you do a fine-tuning of the model and you have let's say, a good data set to do the training and you choose a good model, and let's say that you do a good quantization of the model and you reduce that, even so, the inference for the resulting model, I don't know if it will be fast enough in a general purpose CPU or if you will require a dedicated CPU only for that. And our goal was not to have a dedicated GPU, not even a dedicated CPU for the inference. We wanted to have a process that could consume almost nothing from the system that is already being using the CPUs, the computing resources that has been made available to them. So in other words, if I go to the product, let's say to the firewall product manager, and I told the firewall product manager, yeah, I mean, I have this model, I've trained this model, I've done LoRa, I've done whatever, and now it runs on a dedicated CPU, you only need 60 gigabytes of RAM, and it will provide you that, it will tell me, I don't have that. I have to build a brand new firewall with a brand new CPU to dedicate the CPU to your goal. I don't have that. So I have to go to the product manager and tell him, I mean, this software, it takes, I don't know, 20 megabytes of your memory. It will take 0.0.1% of your computing power, and it provides this value. And it will tell, okay, let's talk about that. So that's the second answer to the second question to your. And the third is, I think that strategy comes with a prejudice, that I think that creating a neural network from scratch, training a neural network from scratch, building a dictionary from scratch, I think that all of that requires, I don't know, 100 PhDs and people that knows about maths, and I have that prejudice, and I mean, it's not, I cannot afford that. What we discovered is that frameworks like, I don't know, TensorFlow, PyTorch, have evolved to a point that you map that with cloud code, and the cloud code, create me an architectural transformer-based architecture in PyTorch that does a self-learning, and you get to speed in less than a week. So I think it's worth the effort for those different reasons.
So
I don't know.
So you're actually using those large language models, but for creating those specialized models.
Sorry, what?
You are using this large language model for creating the specialized model.
Oh yeah, absolutely, absolutely, yeah, absolutely,
In
yeah,
the pipeline.
absolutely, yeah. So, sorry.
So on the topic, you slightly touched on it about changing the dictionary. So, but let's say I had permit deny, and then in a new version I introduce permit with caution, right? So that previous permit splits now in two. How do you have to discard all of the old logs, or do you figure out some way to reuse them?
No, because I mean it's we don't discard anything. The problem is generating enough examples for the new feature. So we already have allow and deny logs. We don't have permit with caution examples. So the problem with us retraining at every software cycle is how to do synthetic data for training. So what we ask our product teams, if you are going to introduce a feature and that feature is going to break my dictionary, you have to be able to generate synthetic data that I can use to train the dictionary on that new feature that you are providing.
But maybe to follow up is that in the first set, let's put it just simply two sets, right? So in the first set you had two sets of the events which were all permit, and in the new set you have them split into permit and permit with caution. So kind of feels like reusing the old data kind of muddles it a bit, or you saw that?
No, the problem is if you don't have enough examples of the new event, and you modify the dictionary. Let's say that you go to the dictionary and add a new entry. Now you have a new token that is permit with caution. Cool, right? I have that new token, and let's imagine that I train the model with this new dictionary, and I don't have a single example of permit with caution. I don't have a single example. What will happen? What will happen is that you've trained the model, and the model has find a way to attend to all the context and decide, okay, if I have a permit here, deny there, blah, 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 this means, and I will map all this context into that point in the space. Now I generate the first ever seen permit with caution event. And it will go to the model, it will go to the dictionary will say, okay, the token for permit with caution is 128. Okay, you put that token and you feed that input to the model, it will generate a vector pointing to a completely unknown point into the space, because it has never been seen that token before. So I cannot afford to train a model on a dictionary and not provide examples for every single token in the dictionary. So that's the real challenge that we have when we're introducing a new feature, and we want to train the model to be aware of that new feature. You have to be able to generate synthetic data that exhibits that feature.
Okay, so last question.
Thank you, Xavi, for the presentation. My question it is about autonomous firewalls. There are three pillars: detecting anomalies, creating hypotheses of why that anomaly is happening, and then remediating using automation. If I understood correctly your presentation, you are focusing on the anomaly detection. I wanted to know if you explore the next step, which is how do you create the hypothesis about what is generating that anomaly, and taking the decisions of which actions to take to remediate, and then acting on the firewall through automation to resolve it, which is going to lead to these autonomous firewalls.
So I don't know if I fully understand your question. So I think that
you are detecting anomalies.
Yeah, but
based on the
forget about
behavior.
firewalls. It's about logs. It could be a server, it could be a printer, it could be whatever. It's generating logs of its normal activity, and I'm basically mapping that into points. This was the presentation was
So
about.
there is an anomaly, yes. And the question is, the next step will be to, when you have an anomaly, to figure out what is causing that anomaly.
Mm-hmm.
So why do I have that anomaly, and how do I fix it, right? So is this something you are exploring,
No, I mean,
investigating at the moment?
So, yeah, absolutely yes. I mean, it doesn't map to this presentation at all. But if you're asking about how are we, for instance, introducing agents in the day-to-day operations of our own SOC, we have thousands of them. Again, I think it doesn't relate to this, but the idea of whenever something happens, something that has been never seen before, that is new, is an anomaly, is a new threat actor, is whatever, and we have to decide what to do with that. The flow before, 5 years ago, was let's expose this to a human, and let's ask this human to make sense of this thing that we've never seen before. Right now, it's not like that. We are in 2026. We've had in the AI era, or the new generic AI era, for 5 years almost, and now the operations, all of them include agents in the.
Okay. Yeah, my question was about how feasible you think it is to complete those tasks on the device. In the same way, you are implementing the anomaly detection in the device to be able to have hypothesis remediation decisions in the device itself.
I think it's absolutely doable. What I think that is almost a no-brainer to do is repeat the same operation. So once let's say that you have this unknown. I've never seen this going to that point into the space, of the state space. So let's assume that either with humans or AIs, you do analysis, a post-mortem analysis of what that was, and then you realize, okay, so this map, this road that the state took from this original point to that original point maps to this specific attack. So once you have that knowledge, that, let's say, a signature, that road signature, it's a no-brainer that you can create a collection of the roads and provide those signatures back to the device and tell the device, if you see yourself walking that route again, ever again, this is the action that you have to take. About me, device, discovering that I'm walking a route that I've never seen before, and giving that walk a feeling that is making me go to a dangerous area with certainty, so certainty that I kill myself, for instance. I don't know. I was just a I've worked in the railway market for a long time, and I always use the same example. If the end of your automation is switching how a train goes, and the decision is put the train in another railway where a train could come on the opposite direction, will you trust how many 9% of precision will you accept before you left that output to the... So when the output of the automation is, let's generate a log, let's send an email, let's generate an alert, okay, I really don't care. But if the output of the automation is, come on, I have to kill myself, and that means going production down. And I'm deciding that because the alternative is me being compromised and all my customer data being exposed. So it's a safe decision, but how certain?
That's what self-driving cars do, or aim to do.
Yeah, exactly. So that's my point. I mean, to that, I mean, we really want to reach that point. We take the example of self-driving cars as an example to follow. So if we have in an era where a human can be inside a car and left alone and let the car drive, we should be able to do the same with operations. I mean, and that's a goal that we have as a company, and we are aiming to reach that level of operations.
Thank you, Chuck. And now we have a legend. We have Ivan Pepelniak. Ciao, Ivan. We have a legend that is going to tell us about, NetLab, and let's see how network labbing is great again. Thank you.
Yes. Okay. Thanks for having me, and thanks for being so flexible. And I'm really sorry I couldn't be there with you because it looks like it's a big crowd, and I would love to talk with you about all the stuff that we're doing. Before I go into the details, I can see the audience, so if anyone is using NetLab, please raise your hand. Three. Okay. For the rest of you, I have an intro what the tool does, so you'll see what it's all about. Forget about my bio and everything. The last line is important. I built too many labs in my lifetime. I hate that, and so a few years ago, I started to solve that problem. So I always use this as an example. It's a trivial. it's a free, totally no strings attached open source project, so you can go and look at the source code. If you want to use the configuration templates from the source code to do your own stuff, go ahead, do it. A few sample projects, there are the labs that we've been developing, and I will probably start adding other projects like the OSPF stuff I mentioned, or Seb just sent me a link to a repository where he implemented Cisco's SD-WAN with NetLab. So if someone wants to do that, we have a solution for that as well. And that's it from my end. I don't know how we'll handle questions, but you can always send me an email and I'll do my best to respond. Thank you. Yes.
Fantastic. We have two questions. Let's try to make it short because we are short.
Sure. Thanks, Ivan, for the presentation. I want to ask about clustering options, because you mentioned that you support different deployment models using bare metal servers, VMs, containers. What about supporting multiple instances in order to support larger topologies?
Not yet. In theory, you could extend subnets with VXLAN across multiple servers, and then start two lab instances on two servers connecting to those external segments, because we support connecting to external segments with lab devices. In theory, Container Lab supports Kubernetes, so you could run the whole thing on a Kubernetes cluster, but honestly, I haven't tried that yet. So, not for the moment. Send me an email and we'll see what we can do.
Thank you.
Hi, Ivan. Just wanted to just check with you, because I know you're a huge Ansible fan, kind of joking there. Are you planning to move away from it, given the latest problems with the deployment that Ansible has had? Yeah, just want to take your opinion on what's your plan with that. Yeah.
My favorite topic. How much time do I have?
Let's limit to 2 minutes.
Okay. Honestly, Ansible 12 and later is, from my perspective, slightly suboptimal. They had to do a number of things for security reasons, and so I'm joking, they had their Windows Vista moment. We are recommending that people use NetLab with Ansible 11 latest. We totally migrated the generation of device configurations of Ansible, so we are now doing them internally using Jinja 2. We replicated some of the Ansible functionality so that most of the device templates we had just kept working. We fixed a few of them. It's all open source, so you can look at it, at what we are doing, and just copy it if it works for you. So we are getting away from Ansible as much as possible, generating device configs on our own, and now we are using Ansible only for configuration deployment, because they have so many deployment modules. For Linux-based containers, we already stepped away from that, so we can configure Arista with Linux scripts as well as the iOS XRV. We can configure Linux and FR routing and Bird and all that stuff directly with Linux scripts. And we have something else. Oh yeah, for many containers, we can create the startup configuration and then just tell Container Lab to use the startup configuration. Although that is suboptimal because you don't see the error messages. And as the next step, we'll just go and use NetMeCode to push the device configuration configurations to the devices. At which point we'll be like 90% independent of Ansible. The only dependency will be Junos because it uses netconf, and I really don't want to reinvent that. And Nokia devices because someone decided to use gRPC to configure them, and yet again, I don't want to go down that path.
Thank you.
Thank you. Ciao, Ivan. So it will be difficult for all the other presenters because now already we got two keywords, AI and digital twins. So now it's going to be hard. So now we have Pere still with the labs, various. Exactly. Our bingo of keywords is getting narrow.
I can put this somewhere around here. Yeah. No, mi sembra que hi ha un botó per fer-ho.
Present?
Sí.
Vols que posi el papa?
Ah, no, no cal. Aviam si funciona.
Si ho he d'acceptar.
No et preocupis. No et preocupis. Okay, so thank you very much for coming. As presented by Paulo, I'm Pere. I work here at the Open University of Catalonia. And basically today I'm going to talk about, my talk is kind of related to what Ivan just presented, okay? So basic, but from the other side, right? So Ivan presented a tool that is meant for, people who are already, trained in networking, in computer networks and protocols, and how they, can, run their labs in one command. We kind of want to do the same, but our objective in this scenario is to actually let the students, break things, play things, understand, how protocols work. And there's one thing that Ivan mentioned, or didn't mention, in fact, that we were missing, right? Which is basically we want students to be able to capture packets, analyze, what is going on in the network, and understand, how protocols work. So I think that Ivan's presentation was really, really good, and I'm actually, using NetLab for certain things. But from the teaching perspective, we think that we are, using a different approach, though what we are using is also supported by NetLab. So it would be like an evolutionary step to basically integrate it and use it if we need to. Okay, so just for reference, this is who I am. You can find me, in LinkedIn if you want. And this is based on the teaching experience for two different computer, oriented network courses that I am teaching. One is for the Bachelor in Computer Science and Telecommunications Engineering, and the other is for the Next Generation Networks, which is for the Masters. Okay, and here we have few problems, right? And one is physical laboratories. Okay, when I was studying telecommunications engineering, we did have some labs. Okay, and it was great. It was back in the 2000s. So we did have some racks like the ones that you can see here. This is not us, by the way. But when I was a student, then I really appreciated those labs. But I also kind of started feeling what were the limitations, right? And so for students, there's an obvious limitation, which is that you can only run limited network topologies, right? Because maybe you have a rack full of routers, but you have 24 students, right? So you can only give a handful of routers, which then means that you cannot build 64 routers topologies, okay? That's the first limitation. Then there's the limitation of the time, so laboratory availability, which means that, well, you cannot run the lab forever. You have 2 hours, so whatever you have to do, you have to do it in 2 hours. Then also there's this high cognitive load, which also Ivan described, which is, well, I want to do OSPF, but in order to do OSPF, I have to connect a bunch of cables, set up the power, all this stuff. But then there's also fear of breaking things, right? Though this fear most of the times was, surpassed by the, ingenuity of students. And then, of course, there is some support for, limited network protocols, mostly because you don't typically run the most, advanced stuff in the lab, okay? But then for professors, when I became, when I started to teach, then, well, you have these 3 things, right? Troubleshooting overload, like you have 24 students that you have to attend at once. Maybe if you are very lucky, you have, an assistant. Then you have maintenance overload, like you cannot imagine what students can do with devices, like erasing the IOS, and then you have to reflash it, and all this, all this fun stuff that takes a lot of time. And then it's also very difficult to assess labs, because what do you ask? Do you ask for, the Wireshark captures? Do you ask for specific questions? It's not so easy. Did you run out? Oh, no. It just entered low power something mode.
No worries, I'm gonna
It's fine. Okay, and then, of course, then for the university, you have expensive equipment and expensive licenses. You have an underused, infrastructure because your lab is only for certain courses and you cannot, reuse it. And then, of course, the e-waste management that you have to go through every time you renew your lab. So when I was starting teaching, I was looking into different alternatives. Some of them I already knew. For example, NS3. Maybe you have used NS2 or NS3, which is good in some sense. It's open source, no licenses that you have to, cost that you have to take care of. It's good for fundamentals, like if you want to deal with, how queues work, how, TCP/IP. You want to go look into the code, but the steep, there's a steep learning curve. Also, you have to focus more on the code rather than on the protocol itself, though it has improved now because you can connect it to Wireshark. And the final point is it's not widely used, okay? Then we have Cisco Packet Tracer that we still use in some initial courses. It's very easy to set up, very convenient. It allows to run the tail simulations. You can even stop and play and pause and analyze what's going on. Does not consume a lot of resources, and it allows you to even create some labs that will be graded automatically, which is nice. Okay. The problem is that this is proprietary, okay, and there is some vendor lock-in. It's only limited to Cisco, and also there is limited protocol support. As I said, we are using also for large labs with advanced technologies. Then we have GNS3, which, well, it's better because it runs and emulates the real network operating systems. You have multiple vendors, and you can integrate it with real networks as well. But it's not so easy to set up. High resource utilization, especially because it's emulated, and the network operating system images become a burden because some of them are not open, some of them are very slow, some of them also consume a lot of resources, so it's not great. We also did some testing with EVE-NG, which is kind of a good balance because it's easy to use. Imagine that like you're in the second course of your degree and you're given a CLI. Students today are not like we used to be 20 years ago, so they are not really tolerant to this kind of environments. So this is nice. It allows you to click, which is nice for the students. It allows to support multi-vendor, and you can even have collaborative labs. Problem is that there is a free version, but it's somehow limited. And also, we still have the same problem with the network operating system images. Okay, so what we really would like is this list, which basically is like, well, we would like to be run into a very lean environment, easy to deploy and tear down. So mainly infrastructure as a code. Support for the latest protocols, support for packet capture, which is something that Ivan didn't mention, which is really important. And then, of course, we also want support for Linux hosts because you want to be able to connect there and ping and do traceroute and whatever you want to do. In terms of technology, well, basically we would like to support as much as possible, going from very, very, very basic IPv4 stuff and IPv6 stuff up to BRFs, eVPN, SRv6, and so on. Yeah. So basically, after doing a lot of testing, we came up with our solution, which is somehow also related with what Ivan presented, which is basically for virtualization. We use a Debian-based VM that we can distribute to students if we want. And we also have our own cloud-based labs that can be used for students to just point and click and deploy the virtual machine where all this stack will run. Then we have the topology management. We use Container Lab, which is also what Ivan presented. And for the network operating system, after playing with different alternatives, we tried FRR, but it works great, right? But for example, we didn't have PPPoE support, which is something that we want students to learn about, or other stuff. And so basically, we settled up with VIOS, which is of course based on FRR and adds other technologies or projects. Then we want a web interface so that students can go and point and click and open the CLI of the router, and it's better than just typing commands there. So for that, we use NetReplica Graphite, which can be integrated with the Container Lab scripts. And finally, for the traffic capture, we of course use Wireshark, but then we use EdgeShark, which is a plugin. It's a container that you can basically deploy in the remote system, and with a plugin in your local computer will allow you to capture traffic remotely, okay? So anything that is running on the remote lab can be captured locally, and then you can use it to save it and analyze it and so on. And for lab distribution, of course, we're using GitHub. So that's our solution. And basically what I wanted to show you is some of the labs that we run. We are not running 64 router labs, but we're doing some of the labs which you can actually try. This is one of the final projects that we have for computer science students, where we give them this topology that will kind of resemble a local ISP that has some access network, some network distribution, some edge networks, then some autonomous systems. It can be an IXP, and then some internet company, which we say it's Google. And the idea is that students will go from scratch, from nothing. We give them the topology, and we ask them, okay, go step by step and do everything until you get it running, and try to troubleshoot it, try to learn what's going on. Of course, we still have to assist them sometimes, but they kind of manage quite well. And one of the things that are also nice is that we can give them like step-by-step things that they have to run, and they can save the state. So if they complete one step, they can save it, commit it to GitHub, and then keep working on the next thing. And for example, for this lab, we have PPoE right here. So we have PPoE on this router so that we have different user profiles. We have QoS, different QoS values for customer profiles. We have eBGP between the different autonomous systems. We have where they can play with routing policies with different BGP parameters. We have iBGP in certain autonomous systems. For example, here we run OSPF. We have CGNAT. We have BRRP, and of course, for the final customers, we have also DHCP plus NAT. So basically, they get to learn and to touch a lot of things. And this is something that runs on a virtual machine that only requires like 8 gigabytes of RAM, something like that. And you can run it and you can deploy it in maybe 25 seconds. So we just give them this script. They just clone the repo. They do CD. And then we provide them with a script and deploy, and everything is working. They can capture traffic, and they can analyze what's going on. Just very quickly. And two other labs that we're running. This is a spine and leaf with eVPN, which this is for the master's level. And so the nice thing is that, of course, we can run the code, and we can show them, this is the commands that you have to run, but we also can capture the traffic that's going through the network, and we can ask specific questions on different network protocols. And then that's the last one that we added, is basically with SRv6. So they get this topology, and we have the IPv6 only underlay. And for the customers, they get to do IPv4. ISIS is doing the routing on the underlay. SRv6 for end-to-end routing, and then BGP and BRFs for the customers. So that's the kind of thing that we're using right now. Of course, using NetLab is something that we have in mind for certain scenarios, but I think this gives us enough flexibility to create different kinds of topologies, while at the same time, not having to go through the trouble of connecting the cables and so on. However, we still believe that having some small lab is really valuable, because otherwise they have like a sense of disconnection between what is going on with the network, where the packets are going, and what are the actual protocols that are running. And that's it for myself. So thank you. If you have any questions, I will be happy to take them.
Yes.
Yeah, perfect.
We do questions during the...
Yeah, sure. I think the coffee break is set already outside. So
Fantastic.
we're fine.
So we have now Xavi from Arista. Yeah. Thank you so much So we start now the part of network automation. So Xavi will tell us their story about AVD, which I think means architect, validate, and deploy.
This year, yes.
Yeah, fantastic. And so Xavi, round of applause also because he's sponsoring our next coffee break. Thank you.
Thank you. Thank you. ¿Podrá pasar? No, vale. Bueno, pues pantalla completa. No, es... Bueno, okay. Vale. Okay, so my name is Xavier Ramon. I want to talk you, I want to explain you how the AVD journey was for us, Arista. So this is a summary of what happened during the last 6 years in Arista in order to be able to bring this solution to our customers, right? So just in case somebody didn't hear about Arista, everybody, okay, yeah, okay, then we can go fast through these ones. Then I will tell you what was the problem, what we were trying to solve, what was the process that brought us to where we are today, what are the challenges and the lessons we learned, and basically how we use it today for us, for our customers, right? So in geometry, if you go to Wikipedia, it will tell you that Arista is this one, but basically we are American network equipment vendor. We do switches, we do our own software for the switches, and we have our own management and visibility tool, which is called Cloud Vision, right? Particular for us is that our OS is the same image for all the devices we use, right? All the switches, the campus switches and the biggest switches, they use exactly the same version, right? The same file. You don't need to deal with different images, right? I had a pretty animation here, but basically the problem that we are trying to solve is basically data center side, where you have an underlay, and then we build the overlay on top of this underlay. So we will build the VXLAN tunnels with EVPN signalization and so on between the different devices, right? So basically what we normally see is around, the enterprise data centers with around 200 physical devices, high-speed ports, 100 gig, 400 gigs, virtualization, as I said, 2 routing instances, underlay and overlay. You need to make the information flow in these 2 planes. And the import reachability has to be announced in the overlay, and then if you do the maths, you will end up with around 5,000 physical endpoints connected to these 200 devices, right? So it's around 10,000 ports. The point is you normally try to have redundant connections, so this is why you have half of the devices. So what was the problem that we saw? If you check before two devices in MLAC, VPC, whatever logical construction between two devices was, which was the core of the data center, was around 4,000 lines, right? If we go to a modern data center with EVPN, VXLAN, 8 physical devices is more or less what it will take to run the same 2 physical devices as before. This goes to more than 10,000 lines, right? And this is a real customer case, right? So that was the problem. The problem is the configuration is exploding in terms of lines, and you are trying to be more efficient, so use less people, and then when you use less people, you still want to perform well. You don't want to be able to break anything because you forgot something, you mistyped something on your keyboard, etc. Right? So that's the reason. What happened was that at that point, we were building several VXLAN fabrics. The configuration is not as straightforward as we saw, and we already had some seed projects, right? So when you are growing into a 200 devices and so on, you are already trying to automate some parts. We had some people using Python frameworks running on WSL, Windows Subsystem Linux. You emulate the Linux on your Windows system, building configuration partially because you can reuse some part of the configuration and so on, right? So we had that already working in-house, right? At the right time, also we had the right people. We were starting with Ansible. Some people had already experience and so on. So yeah, we put all these people together, which are the NR services engineers, so people that are doing deployments, basically. And this is how we build the team to build this tool. So as I say, many engineers, we were building the same VPN VXLAN fabrics. The point is, if you have 10 different engineers, how many configurations you can have? Because everybody can follow what experience they have or whatever, so you may end with always different configurations when you are trying to achieve the same, right? So the first idea that we had was just to base the work that we wanted to do on the data center deployment guide that we had at that time, more than 60 pages long, and it was basically trying to achieve this one: eBGP in the underlay, eBGP in the overlay, use MLAC as high availability, and then include the best practices that we have. Because, well, we all know that not everything is documented, not everything is well known, and so on, and we found some times where maybe for some specific platform you need a specific command that will allow you to do something better, right? This is not enabled by default, and so on. So we wanted to introduce all these best practices. BGP, when BGP starts announcing the networks, if they have to be in the FIP or not, and so on, right? We were lucky, let's say, during December 2020, COVID time, everything was sitting. So we had a week schedule with no projects, just to start working. Well, not to really start working, but start working seriously on that, right? And then we call it Ansible AVD, which was the idea to be Arista validated design, right? That was the first approach. And during the first, and this is how it looked like, right? So we had input variables in YAML format, and then we had different modules in Ansible, right? They were all written in Ansible plus Jinja. EOS designs is the part of the abstraction. Config.gen generates from the abstraction from each device the configuration itself, and both together they do the documentation, right? Because our idea was that every time we do a change, the change is automatically documented in the network. We don't need to have somebody to write a document or update a Visio or so on, right? Everything is done automatically. And at that point, we also had the 2 more roles that were basically used to communicate to CloudVision, our management plane tool, and push this configuration to the running network. At some point, we create also this this new role, was called EOS validated state. And the idea is basically because I know how the network should look like, because I'm saying that in the input, I'm going to check if what the network is really looking like now is really what I decided, right? Imagine that you cross cables. That's kind of easy to spot, right? All these kind of things. We added also hardware and so on. So we were able to see that everything should be running as it should, right? So network readiness for use, automated also. At the beginning, we just had it working, right? We were even using Cloud Vision Portal at that time. The as-a-service solution was not even there. That came later. And yeah, we were using a bunch of YAML files with Ansible, Jinja 2 templates, and so on, right? And then we go with that to customers. Customers say, okay, that's very nice, but okay, how do I use that one? We didn't have any documentation. What if I want to use a different underlay routing protocol because I like OSPF more than BGP, etc.? What if I don't want to use MBLAC? What if I want to use chassis or modular switches? That's kind of funny because the management interface was hard-coded at the beginning. It was management 0 because all the one rack unit devices that we do, they have management 0 as the management interface, right? But that's not the case in the modular chassis. So if you have a modular chassis, you couldn't use the tool. What about versioning? How was the versioning working at that time? I was working on a project. The customer say, okay, I need this command, or I need this abstraction. Okay, let me code that. Yeah, you will have it by the end of next week. And well, you have a new version, and that's how it works, right? And to the other questions, the answer was normally happy face, right? There was no documentation, no other possibility to use another routing protocol and so on. So until version 3, which is like 3 years ago, we focus on documentation, contribution guide, because at the end, this is an open source project. It's on GitHub. Everybody can copy it. Everybody can contribute, and so on. Execution environments, we started building containers for that with the versions already embedded. And we focus a lot on adding new features, right? Because at some point, it was just modify a Jinja 2 template. That's super easy in CLI, right? Because if I have something described in the device, in the structured configuration of the device, which is the first abstraction, I can easily put that into a CLI command, right? That was not so easy for the abstraction part, the EOS designs. You need to have more things in mind and so on, right? So we start adding more routing protocols for underlay, overlay, ISIS, BGP, iBGP. We support iBGP also, and so on. More topologies, as I said, at the beginning it was pure data center, two levels, so spine and leaf, and that was it. And then we started adding platforms, right? Yeah. One thing that was really a recurrent complaint, let's say, was the execution time could take longer and longer, right? So we were able to, at the end, use the Ansible limit flag when executing ABD, so you could just narrow to the devices that you wanted to generate the configuration, right? You didn't need to generate the configuration for all devices. We had many refactor iterations, which can be seen as a bad thing because you are just rewriting what you already did. But this improved the code readability like a lot, so it helped us to go further, and it also solved wrong ideas that were good ideas in the past, which is something that can happen, right? At that point, it was called ABD only, so no more Ansible in the name, and yeah, this is until version 3, right? One thing that was funny was that we didn't have any input validation that came in version 4, right? So if you want to say banana is an IP to a device, it would say, good, banana is an IP to the device. Okay. So we went with the introduction of input validation in version 4. campus topology. We introduced also a versioning and bug fixes policy. We have a cadence now that you know when you can expect, you have some predictability in terms of when the new version is coming out and so on, right? And we also did some changes in the input structure. We were using digs of digs at the beginning, and we changed that to list of digs, right? I will explain you later why, right? We also did the PyABD, and we changed this EOS, the configuration deployment. It was changed to CB deploy, and we did the introduction of ANT as a validation role, right? The validation role before it was Ansible with Jinja. This is Python, right? PyABD is also Python, and CB deploy is also Python. The only thing is that we made some changes in Cloud Vision, so that's why we needed a new role, right? And for version 5, we did some improvement in the input validation and the error messages. Before, it was saying there is an error here, and sometimes didn't even tell you which line, didn't give you any information about what was wrong. So yeah, everything had to be right, and if it's not, good luck. So we improved this in version 5. And then we did the deprecation of all roles like the validated state based in Ansible and the EOS config deploy CVP, also based in Ansible. So this is how it looks today, right? The EOS designs, it takes the input, it generates you a config per device in a structure, in YAML, and also the documentation, right? And then the EOS CLI config gen, what it does, it takes this device, these files that we generate here, and then we generate the configuration and the documentation for each node, right? You don't need to use both of them together. If you have your own abstraction and you want to use it only, if you want to define your YAML files and then let us build the CLI, we can also accept that, right? The challenges and the lessons we learned developing this. The goal was clear for the beginning, so we had an endpoint at the very beginning, right? And it was just being able to deploy the solution guide, the deployment guide that we had, right? Including the best practices that we were learning in the field. We helped adoption because even we had a very rigid design, the solution was working, and it was accepted by many customers. The learning curve to add new features was not steep. So if you need a new CLI comment and so on, you could do it yourself. It was not that difficult. We changed to a single configuration file per device. This helped us to just being able to show which are the difference in the configuration. If you have it in different devices, it will be much difficult. And for some customers, it was kind of tricky for them. The ABD showed what was being deployed on other customers, right? So at some point, if something was not in ABD, it meant that nobody else was using it. So you want to be the first one trying something? Yeah, maybe you want, but normally it's not like that. And at some point, it was also important to, I think the trust is built also by saying, if you don't feel comfortable, if you don't want to use it, you can always unplug it, right? So we never close the CLI to anything, right? So if you want to configure using the CLI, you could always go back to do that. I think I never saw a customer doing that. The main challenge that we saw recurringly during times was the execution speed, right? We narrowed that down to Jinja 2 processing. So at some point, we were able to put the description of an interface using a Jinja template. If you were using this option, 30% of your time was going there, right? And the organization of data. What I said, dictionary of dictionary was 100 times slower to read than a list of dictionaries, right? So everything was adding up and taking time. And then we had if you go to the corporate wall, there's always all Windows workstation where you have to do everything. WSL, everything was adding up, and it was very inefficient. Some customers were pushing us to AAP, Ansible Automation Platform, because this is what they use in-house and they want to use that. Yeah, but they were using that with minimum requirements, right? If you want to just push a command to a device, maybe 4 gigs of RAM is more than enough, right? If you want to do that in 200 devices. If you want to generate the configuration, talk to a different system and so on, the time was also being consumed there, right? So we changed that to Python. So we are still able to execute using Ansible, but the core is changed to Python, right? So if you change to Python, when we changed to Python, we saw around 50% reduction in the time it took to execute. And then for the ANTA, so the validation, we also reduced to 90%. So a customer was using before 50 minutes in the EOS validated state. With ANTA, it was using 5 minutes. And it's running thousands of tests, almost real time, right? So how we use it today still is used almost in every deployment, right? It gives you best practices out of the box. It allows us to really achieve faster deployments. It gives us certainty and flexibility in the configuration. So I personally use it even when I have a very small network, like 6 devices that customer wants to configure. You do that into an AVD inventory. If tomorrow customer comes and say, hey, I want 10 new VLANs, the effort is much simpler, much less than do that everything manually, right? Even if it's just 6 devices. Yeah, we are able to integrate that, or we integrate that with CI/CD pipelines, digital twin, so another tick in the bingo. Yeah, we are also able to generate digital twin configurations. And finally, after some years, we have a dedicated team to develop the tool and to support it, and we are also even offering tax support on this project, right? Yeah. And basically, that will be the presentation. I don't know if there are any questions.
Any questions or maybe?
Can you remind me, what does ANTA do for validating the network? That do they parse? Do they do telemetry?
It connects to the devices.
It connects and runs show commands?
Yes.
Okay. And it parses the show commands?
Yes. You can also do synthetic testing, pings.
And I have to ask, even though you might be tired of this question, but why don't you use stuff like netconf and for validating the configuration, which will save you the dictionary, the model, basically the model validation?
No, so the point for us is we already have the
You already have the infrastructure, so there's
yeah.
no need to modify without new features. Perfect.
Yeah.
Thank you.
Okay.
Okay. Thank you.
So we go to the coffee.
Yeah. So yeah, we have the coffee. So thanks again, Xavi, for
Let us invite you to a coffee.
that. And we have a 30 minutes coffee break, right? Yes. Perfect.